Sure, we don't have her in here.
Patricia's here.
Oh, she's here.
Mic test 1 2 3.
Oh no, she's not here yet.
Okay, we got Daniel, we got Andrea, we got Harry, Takashi, David. I don't know about Lou.
No, also didn't specify.
Jason's not here. I don't think Ross.
No, Russ comes with Jason. But he's not
Okay,
here yet.
and Shree's here. Shreeni's here.
Just gonna make it
probably
plain.
just not on the screen.
Yeah.
So
So
we-
so anyway,
Something in the
Joseph,
grant that says
the
we can't
head,
do that.
whatever he is, downstairs waiting for people.
Okay.
I'm gonna send him up. So Travis, Joseph is really sweet. He's waiting for people to let him in. We look like we've got
Oh, that's
4
great.
people that aren't here yet.
Yeah.
Get my
And-
presentation last night.
Okay.
There might be like a few
I have to
students
both
and
there.
We
stuff
just
like
got
that.
an email
So
from
that was because the
Patricia.
Wi-Fi was
Okay.
cooperating. It uploaded twice.
Okay. Yeah.
I think they're both.
Test 1 2 3.
It doesn't matter which one you pick. I'm going to say in the middle of it that this is the wrong one.
Okay. Good. I have both there.
This is my streaming link.
Is there a restroom nearby?
Yes,
Yes, you have to go back out to the main hallway.
Okay.
but there's a unisex one right on your right. So
Yeah.
if you kind of do a right wall following. Oh, so very rare to get all of the different agencies and groups together to actually do something like this. So we want to show up there on time. So we're going to, but again, we want to form a network. We all want to meet each other and talk. So we're not trying to shut that down so much as keep us on there. So we're going to leave here at 11. We're going to get to our walk effectively to the little shuttles. We're going to have a great lunch, quick lunch, and get out to there. And then the rest of the day, then we'll come back to their location. We'll have breakout groups. Right now, we kind of have 4 breakout groups. One thinking we're either going to be, some of you are working on machine learning, deep learning, computer vision stuff. Some of you are doing GIS time series stuff. Some of you are doing unmanned system stuff. Some of you are doing decision aid stuff. We may have a 5th one, or we may reconfigure later on. But the idea is at the end, we do that breakout sessions, think about what it is we need to be doing as a community. Of course, the obvious answer, what do we need? More money? Sure. But more than that, is it test beds? Are there certain key research gaps that need to be highlighted? So have that thinking about how you can be successful and your colleagues, and how to do this as we go forward. So as we continue to, you know, we haven't even gotten to tried my presentation yet, and with a name like Murphy and Murphy's Law, oh look, see, yours works, so now mine won't. It's certain. So let's just go ahead and do a quick introduction, and if you're on the program committee, please also identify yourself. And we'll start with Travis, and he's doing all the local arrangements. So you haven't met him yet, but yes.
So I'm Travis. I'm the faculty representative from HILO here, and I'm really excited. I'm assistant professor, and really excited to be a part of bringing this workshop to life.
Now, are you in computer science?
Computer science.
Okay, so this is going to be nice to see the interdisciplinary. So be sure and tell what department you're from. Okay.
Hi everyone, my name is Trisha Chafee. I'm a PhD student at the University of Southern California. I'm excited to be learning more about natural disasters. We're working on a project with human-swarm interaction and search and rescue. So I'm in computer science.
Okay, good.
Hi, my name is Lou. I'm a student at Virginia Tech, and I also work at a startup that does time series analysis. And I'm excited to get to know everybody here. I'm mostly working with statistics and time series, but I'm obviously interested in the field as well.
I'm Sean Cleveland, University of Hawaii. System, ITS cyber infrastructure group, background, computer science, bioinformatics, and high performance computing, cyber infrastructure, gateway construction sort of stuff. So.
And Sean's also been working on the program committee, so he's been helping. So there. All right, David.
Hi, David Takayama from Oceanet. Oceanet's a local Hawaii-based research and development company, and I'm IT.
I'm happy for you there.
Cool.
Hi, Matt Baldwin. I work here at UH. I'm actually staff here in the library with the Cyber Canoe and technology, but I'm currently applying for grad school in emergency management, infrastructure management, so personal interest.
Great, thank you, Matt.
Hi everyone, my name is Abu. I am currently a PhD student, 3rd year at Stanford. I am in computer science. Our lab develops machine learning methods and general methodologies depending on what data sets we're working with. Historically, that's been medical data sets, but now we're interested in issues like computational sustainability. And so I'm here to learn about the data that is present in the type of data that you guys work with, and hopefully developing methods that can help with some of that analysis.
Okay, let's keep it all short. Just who you are. We know why we're all here, because we've got a lot of people to go and we have time to talk. But no there.
Hi, I'm Andrea. I'm a postdoc from the University of Padua, working with decision theory and machine learning.
Alex Wang, assistant professor of computer science at Texas A&M University, one of the program committee, although I have been helping minimally. Robin did all the majority of the work.
That's true. That's true.
Adair did all the work. But the NSF grant that is helping partially fund this.
Okay. I'm Takashi Miyamoto, assistant professor in University of Yamanashi in Japan. And my department is civil engineering. Nice to meet you.
Great.
Hi, I'm Kayla Shakir. I am an undergraduate student here at HILO, just here for this section.
And you're a computer science?
Yes, I am.
Oh, very cool. Great.
My name is Harry McElroy. Thanks for putting this together. This is great. I'm on the industry side,
I'm with a company performing this corporation, and our focus is on artificial intelligence for operations and logistics. And we do collaborative research with a lot of universities.
Great.
Srini Parthasarathy, professor in computer science and engineering and biomedical engineering at Ohio State University. We work on hurricane-induced flooding, mapping, and
my name is Yolanda Gill. I'm from the University of Southern California, computer scientist, and I've been working on using AI to integrate geoscience models from climate, hydrology, agriculture, economics.
And Yolanda is missing two important things. One, she is president of AAAI, and we would not be having this workshop if it were not for her. It would not be associated with AAAI if she had not said, this is exactly what we need to be doing as a society. The time frame's short, but let's do it anyway. So again. And then she said, oh, and get Travis. So there. Right.
I'm Suzanne Pierce, and I work at the Texas Advanced Computing Center at the University of Texas. I'm a research scientist. I'm actually a geoscientist by training, and I work in decision support development and participatory modeling. And I'm leading the development for a science gateway platform for Planet Texas 2050, where we're trying to do something similar to what EKVI is already working on, and getting all of our Texas data and information and models so we can start to integrate and use them to learn.
So cool. Look how much diversity we've already got. It's not just all the usual computer scientists. So we've got industry, geo. Yeah.
Hey, I'm Francis Cristobal. I'm the IT admin for the computer science department here at HILO. I also do the majority of the cyber canoe implementation. Interested in data visualization research. So we partner a lot with UH Manoa and their Lava Lab, and also work with EPY and Travis there.
I am Daniel Garijo. I work as a computer scientist at ISI with Yolanda, so USC as well. And my background is on semantic web. What I've been working on is also model integration and capturing the metadata and the knowledge behind all these models so we can integrate them together.
Hi, I'm David.
You failed.
You said short. I run the Center for Disaster Risk Policy at Florida State University. You'll hear more about me later.
Hi, I'm Odair, research associate, and I work under Robin. And I'm the person that was sending the annoying emails to you guys the past weeks.
He's been the one doing all the real work. Okay, well, why don't we go ahead and get started? We have 4 groups of talks that are kind of tutorials, background from more of the program committee, and then we're going to get into the great lightning talks. Yolanda.
Can I say 5 sentences?
Absolutely.
Okay.
But you have to stand up where everybody can see you. We're getting a lot of seeing everybody's back of everybody's head, which is not.
So I want to say that we have an opportunity to get more money, get more attention, get more resources, and give this area of research in AI more of a stage. I am chairing a national AI research roadmap for the next 20 years. And accelerating scientific research is one of the areas, but also improving society. And so I think there's a lot of societal benefits and scientific benefits to this. We're talking about not only the science that is required, which I'm sure many of you are interested, but we're also talking about having a national AI platform with AI services and AI-ready components that other scientists, but also small industries can get involved with. So we don't want AI to be just the property of the Googles and the Facebooks, but to be the property of everyone. So anything that comes out of these discussions, I just want to say that I'm listening and that you all have a chance to give us inputs and information that we can include in this roadmap report. It's going to the government to make decisions about funding priorities. So if this is an opportunity for anyone, this is a good time to have this meeting for that reason also.
The breakout groups. This is why this is so important, that the report that we'll put together from this. All right, Atlas, you've got about 10 minutes. Let's keep it 10.
I saw that other thing.
Yeah. We also say we're going to start at 8:30. So
I'll try to be quick and crisp.
You can have 5 of mine.
Where is my slides? The first one.
Where's the clickers?
How should it control it? Oh, okay. Sweet, thank you. Okay, so hi everyone. I'm very happy to be here as I have been working with Robin for a while on how to apply our computer vision and machine learning techniques to help the net disaster response. I have to say that I mostly work on the perception side, and I look forward to be more closely integrated with the decision-making side. I'm an assistant professor of computer science. So our work from the computer vision side has been motivated by several new platforms and its raising challenges, and we view those challenges from a unified perspective. Several platforms that we have been focusing ourselves on. We partner with some industry companies to work on autonomous and assisted driving to provide them perception systems like segmentation, detection, tracking. We work with a few government agencies, including the Department of Defense and the Department of Agriculture, to provide them drone-based computer vision abilities or post-analysis ability of their captured imagery. We work with surveillance makers. For example, we have a major project with NEC Labs to improve their surveillance robustness to sustain over all the lighting variations, all the weather variations, and the robustness to low resolution as we have always been suffering from surveillance videos. We are also recently entering the area of smart home cameras and IoTs to improve the efficiency and privacy protection of computer vision techniques. So looking at all those diverse platforms together, we find that those newly developed computer vision algorithms have put off-the-shelf solutions into jeopardy from several perspectives. As I summarized, of course, there are more. So the first challenge we observed, which I think may be particularly true for applying computer vision in the disaster response scenario, is they are no longer operating in perfect quality imagery, not even reasonable quality imagery. They are working on very poor, very bad, arbitrarily bad quality imagery. So like UAVs, I can tell you that I get unbelievably bad quality imageries from our partners in Army research. And that could, I guess the situation will not be any better if we get real imageries from serious disaster. I will show you some examples I got from Robin kindly. So the uncontrolled and complicated visual conditions we have to capture those images in outdoor environment make a serious challenge, while many computer vision algorithms trained either by synthetic dataset or controlled quality dataset totally unable to be used in those real data. The other related question is, now, we all know that ImageNet can reach very high accuracy, but that is based on training and testing ImageNet models on a super powerful server and costs a lot of battery powers. But what if I want my perception system to be integrated in the front-end mobility devices like UAVs? Well, the battery is limited, and I have to be as economic as possible to do a robust decision while saving my energy, accelerating my inference time, and make my model compact so it can be loaded in the mobility platform's memory. Those efficiency issues, as complementary to the first robustness issues, has made another aspect of our research. We broadly related, not quite related to that response, we are also interested in how to improve the computer vision's ability to enter into the high security and highly trust-sensitive applications, including biometrics and in-home computer vision. But let's skip it for today. I am mostly focused on 3 applications. We have a broader picture than that, but I'll try to be more focused today because Robin is not kind enough to give me more time. Well, so 3 applications which we want to supply as our off-the-shelf tools to disaster responders. Dehazing, derailing, and light enhancement. 3 non-classical, but I believe as practical tools. So I especially like the acronym of the 3, DDL, deadline, which you may agree with me or not, are the major driving forces for computer science in their productivity. And the thing I would like to bring to your attention before going to technical detail is, if you come from a vision background, this may look like you look like to you similarly as a denoising or super resolution or other image enhancement techniques which you are using daily from Photoshop. That is partially true, but that's not absolutely true. Looking at those three applications, in many cases we have to call for the removal of haze or rain or enhance of low light conditions. We are not really wanting the image quality to be visually better. I mean, sometimes we are, sometimes we are not wanting those image quality to just be better for human perception. Thinking of the surveillance videos or many other drone-based videos, they are not collected for human view purposes. Think of the 24 hours security surveillance in any campus. Will anybody really bother to look through all the video data? They are just for intelligence analytic consumption. So to ensure those data to be suitable for intelligent machine learning and AI algorithm at the backend is as important as to ensure they look visually pleasant to person. And many of our experiments provide empirical evidence those two goals are not really aligned with each other. So you have to consider different goals based on the purposes you want to use your data. Okay. I will get more focused on talk about our effort in denoising, and I want to make a mention that our dehazing algorithm has been kindly integrated by Robin and Adair in the imagery analysis toolbox for disaster response. I suppose Adair and Robin will give more introduction of that part. So I just go through the algorithm briefly. So the key point, we look at the dehazing problem, which make it technically different from traditional image enhancement problem, is more complicated than introducing just noise or motion blur or downsampling. That's the traditional research subject in image enhancement. Those degradations follows a relatively simple affine transform form. But talking about rain, talking about haze, talking about low light with iOS noise, I guess it's hard to imagine those complicated degradations could be described as a linear model. And actually, those real models has been heavily studied by our colleagues in atmospheric science. And we are borrowing some research results from them. For example, this one is called atmospheric scattering model. It's a scientific model developed to describe the generation of haze. Without going much of details, briefly, it means that the visibility of an image on the haze is related to three factors. First, how dirty the air is. Second, how far away the object is from my camera. And third, how reflective the object's surface is. So roughly and empirically. And we have some quantitative ways to decide them. So traditionally, dehazing has been researched, and I'll tell you how is the traditional way to look at it. As I said, there sounds like to be three hyperparameters to decide the visibility of the image after going through a haze degradation. So traditional method use some physical and empirical method to estimate those three hyperparameters and then take them back to that atmospheric scattering model to compute the clean image, just like an inverse problem. So the motivation we are working on this problem is we feel like we want it to be more data driven. We want it to compensate for the long tail effect that the physical model may not be able to fully capture. But we also do not want to throw away the important physical knowledge as we believe they're important for those atmospheric related degradations at the list. So our rough idea is to develop a deep neural network. Well, it is highly structured and physical-based. The basic idea of this deep learning model is we use a small neural network to estimate those physical hyperparameters and design a new layer to compose back those hyperparameters into the clean image. So we are able to train the entire neural network whose structure was inspired by the atmospheric scattering model in an end-to-end fashion. And we are able to prove its superiority in all the ways. So, and we further, as I mentioned in the beginning, to optimize the task, not only for dehazing, for premium perception, but also optimizing dehazing as a processing step for object detection, as the usual case in application. We use graphics rendering techniques to render some dataset with both detection annotations and haze, which the original image looks like right and the rendered image looks like the left. We trained our model by concatenating our dehazing model with the off-the-shelf detection model in an end-to-end fashion and apply it directly to the practical data. This is a traffic surveillance data from Beijing City, where we get a connection from them, and you can see that compared to the original detector, which result look like the left, our improved detector can look like the right, and is actually now deployed in their their traffic surveillance system. I have some demo to play, but I would rather skip and directly go to this Vogue remove image, which is the result of our algorithm in the real disaster images. So I got those images from Robin, and we directly tried our dehazing algorithm on top of that. The result, I would say, preliminarily encouraging. The image we get from the left column are those two, for example. I didn't cherry pick. And the enhanced result by our algorithm looks like the right column. It's not perfect, and I can tell you that if I get a fully cloud image look like this, I don't have a magic to recover back what looked beneath this. But I guess a better job could be done if we consider a video case, and we are actually now developing a video dehazing algorithm dealing with those highly heterogeneous and dense fog. Just give me, we built a data set for that. And just to display another capability, we recently also developed an algorithm for another industry company to enhance the images. So it's a lighting enhancement, and it has been designed to be fully adjustable to overcome all the overexposure and underexposure. Images coming to the model are like this column, and this one. And I promise you that no hyperparameter has been tuned ever in this process. It's a one-click intelligence lighting enhancement. And we're able to automatically enhance all the underexposure areas while not introducing any overexposure artifacts. So this is to develop for a video app, actually. But we look forward to introduce this capability to low light nighttime UAV videos. We want to give a try. To give you a preliminary idea how it works, we have already applied the algorithm in our autonomous driving partner, and this is autonomous driving enhanced video. So the input is the left column, and you can safely ignore the column from the column 2 to column 5 if you don't care. This is our intermediate comparison method. And just get a focus on comparing the leftmost column and the rightmost column. The right column one is a light enhancement introduced by us. So we are not only able to enhance the visibility, but also suppress the artifact caused by the dirt and the dust in the camera lens, which I feel positively surprised. And I think I want to talk to more people if you have real challenge data for us to give a try, as we are quite flexibly adjust our model to adapt to your case. I guess that's pretty much everything. So our capability has been have won some sweet awards in past years, CPR and ECC challenges like this one. We use our algorithm to enhance the UAV imagery captured by our AirPods supported challenge, and we won this challenge by enhancing the video first, and we also won the challenge by enhancing the images captured for forensic purposes. So overall, I just want to show that we are enthusiastic about enhancing realistic imagery, and hopefully our capability could be of use to this community. That's all for my talk. Thank you.
Okay, Suzanne. All right, and thank you. And while they're sitting up, quick question. Any quick question for Atlas? You'll be able to see him throughout, but
I will be able.
Okay, yeah.
You probably know how to navigate it faster than I do. So that was a lot of fun and really interesting. In some ways, I wish that I got to speak at the end, because I usually like to process it and listen to what everybody says and then try to synthesize it all. But already, just listening to Robin's welcome and speaking to the fact that there's a need and capability to deepen the conversations among this community and in a sense extend and create, thank you, the community and build the relationships. My theory of change for the social scientists in the room, if there are any of you, is based on relationships. So I really think that building the relationships is the way that we start to actually make progress and advance. The technology and the information is all secondary to what are these connections that we're able to make. And then what Yolanda mentioned about this idea of an application-ready national AI platform, there are people in this room like Sean who are implementing those right now, which is just absolutely incredible to watch because it seems like it's on an accelerating path with all of the efforts in the science gateways and the portal communities that are happening right now. And what we see, at least from the geoscience side in the EarthCube arena, which is a national science funded effort, is a lot of component capabilities are starting to come together, and we're able to start to put them together to create not a super platform, but certainly the next generation, more advanced platform, I hope. Is that an accurate way to put it? And I feel like Sean is at the cutting edge, and Ike Vai is definitely at the cutting edge of where this is going. And then I really liked what Dr. Wang said about algorithms in the real world. One of the reasons that I'm here today is because I want to talk to you about the Intelligent Systems for Geosciences Research Coordination Network, which is NSF funded. It started in 2015, and it is a group of geoscientists or earth researchers, earth science researchers, and computer scientists. And we actually just hosted a workshop here that some of you attended in August, so here at HILO. And here's just a quick overview of some of the groups. So we've got a pretty nice national representation, and in addition, we've got groups that are international, and we've got committees that are in work. And so what I want to offer to the participants in this workshop is this may be a way to link together to broaden your conversation even more. We would be thrilled to be able to help support the efforts of this workshop moving forward. So what is it? It is intelligent systems and geosciences, with the goal being that it's not AI in service to geosciences, but it's actually AI and geosciences coming together to find the cutting edge problems that everybody's winning. And it includes all of these areas. So AI and machine learning, semantics and metadata for reasoning, geospatial computing, information integration, robotics and sensing and vision, and knowledge representation. On the earth sciences side, we've got members that are from near surface, ocean, polar, deep earth, atmospheric, and geospace. For any of you who are familiar with the layout of NSF programs, that's not going to be very surprising because it pretty much laps right over the way that NSF is organized. But the goal is to get us into a room so that we can start to look at all of these complex, big, broad, uncertain, ill-structured, and dynamic problems that we've got in dealing with the kinds of data, information, and knowledge that we need to handle to get meaning and better understanding and learn about our Earth systems. So my long version of this goes through a subject matter expert lecture series where we have experts that, oh my goodness, time goes fast, where we have experts that have touched on all of those different kinds of data problems and how to address them. And so that's an online YouTube channel, and we do a monthly call. And what I want to tell y'all is we've got training institutes, we've got resources that we're starting to share. It's a highly collaborative organization. It's jump on board. If you want to be part of it, jump on our next teleconference call, join our listserv. You can go to the is-go.org and you can start to find more information. We are planning our next hands-on workshop. It's hopefully still going to be in Boulder, Colorado, and we've just had to change the date because of the federal furlough. And so we're going to probably do it sometime May or June, we hope, in Boulder, Colorado. And then in 2020, we're already will be hosted by Oregon State University. We're sharing curricular materials, and there are publications that are coming out about what we know and understand after a survey of national programs for teaching AI and geosciences together in a room. And we just launched, and this is something I think it's worth talking about with this group, we've launched a fellowship program and a team project pursuit program where, in this case, this is a fellow that we can support you with travel, and we actually have some corporate sponsors that are interested, and if there are corporate sponsors in this room that would like to have a fellow come work with you from our organization, we're 200 strong, and so this is, you can find someone who's working in your area, and we can help to support their travel costs or help support their work on an area of interest or on your data. And then the project pursuit teams are getting computer scientists and geoscientists to really work on a project. And one of the projects, there are a couple of things that have been happening from the Hawaii workshop. We've actually got some real-time data streams that are being fed into integrated models. And the integrated models came from a lot of the first workshop that we held in 2017. And with that, I am out of time. So. Open for more conversation.
Get to the next. Here, I'll let Jared do this. So Jared's actually a part of our EKY team. He works on one of the decision support tools that actually leverages our gateway. So he'll get us set up. So I'm talking about our gateway. It's actually a science gateway. So science gateways, if you're not familiar, are essentially places that have shared data, shared software, shared computational resources, shared instruments, a lot of shared things that are sort of centralized for a research community to sort of have access to and help leverage the research. So I'm Sean Cleveland, Jennifer Geis, Gwen Jacobs, they also work with the platform. Gwen Jacobs is our Director of Cyber Infrastructure. So EKY is the project that people have been throwing around. EKY means knowledge of water in Hawaiian. And so the driving force behind the project was in reference to water, how is climate change going to impact it? How are incidents going to impact it? There was a Red Hills spill of jet fuel for these tanks that were buried. It went into the ground, and people were like, where's it going to show up in the groundwater? They've never found it. Growth and sustainability. They want to build houses, new hotels, stuff on Kona, on the islands. How's that going to impact water? Are we going to start drawing salt water from the ground? So the idea is to build this gateway here to bring all of this information, all these pieces of different data, geophysics, geochemistry, rainfall, well monitoring, agency and legacy data, kind of into one platform and combine computational tools, software tools, and the data to give access to that stuff to the scientists, and then take their data products, feed it back into the system, and offer additional tools for doing decision support and other informatics and analysis to our water managers and our decision makers, as well as giving that information back to the community, because that's where the information kind of originally comes from. So what we currently provide, we built our gateway on top of the Agave platform, so we partner with TAC, as well as the Science Gateways community. ISGeo is also a partner, so they're interested in leveraging this stuff. So auth permissions, web, mobile, REST APIs, we're offering so metadata, data annotations. We currently got 14,000 annotations for data, 700,000 values, 40 million values for some other data we got in here. Search and discovery, spatial, temporal, full text indexing on some of our stuff. Computational workflows, we have bioinformatics stuff, rainfall, subsurface water modeling, all these sorts of things. So this is an example of the interface. This is the decision support tool. Jared McLean back there, he's been building this with the USGS. So this is USGS's rainfall recharge model under 2 different climate scenarios, the last 30 years going forward into the future, and then the RCP 8.5 report from climate change. So people can change the different ways that land use is sort of defined and see how it impacts recharge for the island. So this is important for a lot of our water managers and stakeholders. This has got 40 million recharge values over this raster, 75 meter cell resolution here in this map here. So that's an awesome project Jared's been working on. Tom Jambaluka, Matt Lucas, Ryan Longman, they've been working on generating monthly to daily rainfall maps from a bunch of aggregate data, satellite data, and that sort of thing. So that's also part of this platform. So future work, we talked about time series, sensor data collection. We're integrating that into our platform with Chords, integration, dissemination into HydroShare and some other places. AI opportunities, we're looking at, finding legacy data sets that, sort of match and bring them into the system with sensor data, alerting trends, patterns, recommendations, some automations on doing some different things. Data search and discovery, being able to do recommendations for researchers who are like, if you're interested in this, maybe you like that, sort of like Amazon. So I think there's a lot of that kind of stuff. So with that, I'll hand it over to Travis, who's also a part of the EQI project.
So I'm going to be talking about just a little bit of my work that's kind of loosely related to natural disasters on Safe AI for efficient data collection, all work that was done here at HILO with myself and a bunch of undergraduate students. So we really want to think about AI systems. We're all very interested in AI, and they're getting more and more powerful. They're being granted the ability to do more and more impactful things. And this is particularly true when you want to involve an AI system in sort of an emergency response setting. And you give it all these abilities, you have to think about the safety side of the equation. There are certain things that you never want to do that are unsafe, and how do you prevent it from doing those unsafe things? And we're all interested in machine learning, but simply learning from experience what things are unsafe, you don't actually want to try an unsafe action in the real world in order to know that it's unsafe. So that's not very attractive. And so what typically is done is that you have a small group of AI experts sit down and write constraints on the system to prevent it from doing these unsafe things. However, this is, this puts a lot of burden on those experts, because if it's defined incorrectly, that's going to result in unsafe behavior. And so really the weak link is not so much the machine learning algorithms or the AI algorithms, but really thinking about the human side of the equation and how these things are specified. So one thing that could be improved here is, well, why are we only looking at a very small group of experts? Experts could have, they have expertise in AI, but they could have certain collective biases, blind spots. A small group is going to have really a lot of difficulty scaling up to large problems with complex state action spaces and so on. So in addition to making the process better, how can we make this more accessible to people who might not be AI experts? So we did this project with myself and a bunch of undergrads where we developed a lot of general purpose task designs that were successfully made this process of specifying constraints more effective and more accessible. We tested it on an important real-world educational problem, but the work was general enough that it could apply to many other domains, for example, things in natural disasters. Another thread of related work I've done is on, or working on that right now actually, is on human-in-the-loop data collection. So especially with natural disasters, how you collect the data is often one of the most important parts. Before a disaster occurs, you want to be able to get some information that predicts that that's going to occur, and that requires sensors and drones being set up in the right places. You've also got to think about, while the disaster is occurring, and we saw this here on this island, civil defense and so on, we're trying to update that map and keep everyone informed about what's going on in terms of the current disaster situation. So we're working with ISGO and others to sort of look at this process of human-in-the-loop data collection of, how can you make sure that your drones or your sensors are actually going out there and collecting the most interesting and useful data? And how do you determine what's interesting and useful? Well, you've got to get feedback from human experts and scientists and so on to do that. So I think this is a really interesting and understudied problem that I'm excited to work on. So that's all I had.
Okay, so who's next?
Oh,
is it David? Oh, okay. I thought that's it. Okay, great.
Yeah.
I thought y'all had one more.
Yolanda, but I don't know if...
Was Yolanda were you going to present? No?
Okay.
Oh, okay.
Okay.
Okay, great. So now we're
Just
doing
want to make
data.
sure we weren't
Great.
shorting you.
We didn't want to get the ISGO.
This one. Right.
Miss someone.
I feel like I've proselytized.
All right, so good morning, everybody. My name is Dave Merrick. As we mentioned before, I'm also the one that doesn't fit in this room. I'm not an engineer. I'm not a computer scientist. I'm an emergency manager and a logistician. So that's my background. So my team at Florida State, we're the Center for Disaster Risk Policy. We are practitioners as well as academics. So we do teach classes because they make me. But what we actually do is we do manage disasters. All of my faculty are responders. We all have state response roles, local response roles, everything else. So that's where my talk is coming from, and this isn't even the 10,000 foot view. This is like from low Earth orbit that we're going to talk about here right now. Those of you that are stuck with me in the van, feel free to ask me as many questions as you want about this as we go through the day. So. I'm also on the board for CRASAR, Center for Robot Assisted Search and Rescue, which you might all be familiar with. It's Dr. Murphy's organization out of Texas A&M. So real quick, the challenges that we face it's everything. Okay, so this is an image from Hurricane Michael. I can't really tell you what the top 10 challenges are because it's easier to tell you what works, okay, than what's broken. And this is true in just about every disaster that I've worked, and I've worked dozens of federally declared disasters of all types throughout Florida. We're going to focus on the last couple of years here. Just a point here, this damage you're seeing for Michael is all wind damage. This was not from surge at all. So we'll get to the surge. That is surge damage, right? So you can see, I don't have a laser pointer, or do I?
Yeah.
Whoa, look at that.
Hold it down.
Hold it down. Hey, that's really. Okay, I'm gonna want one of these when I get back. So houses went all the way out to the surf line here. These are foundations of homes that were built on slab instead of elevated. Mexico Beach, which is where this was, is an older beach community. Certainly not built up to current code, but that was part of its charm. But as you can see, all of these homes, they're just toothpicks. As you move north, that view is looking south from just about US 98. So this is the environment you're working in. This is the environment you're trying to collect data and make decisions in, and it is extremely challenging. So I'm not going to play the video because I'm probably already out of time, right?
Too bad.
Okay. We'll still skip it because this is more of the same. And then we have, I was part of the Crazar team that deployed here in May to work for HILO in Wayne County on the volcanic eruption. And that was a unique thing. So, if you go back a few slides, that's what I'm used to, right? If you say disaster, that's what I think hurricane, I think tornado, I think flood, I think wildfire. This was definitely a new situation for us, but it paralleled all of the problems that we have in other types of natural disasters regarding communications, coordination, gathering good data, and making decisions. So, and we've flown over 350 sorties in the past 2 years on 4 major disasters, 3 hurricanes and a volcano. The types of work that we get asked to do, okay, and let me pause there for a second. So one of my roles for the state, oh wow, that's like having a week left. All right, that's awesome. So
I feel like I may have empowered him too much. Okay.
Maybe I can slow down a bit.
Breathe.
It's overrated. So one of my roles at the state is actually to work in the air operations branch for the state of Florida, which means we work pre-impact and post-impact to coordinate aviation resources and meet whatever mission needs are being given to us. Okay. Air operations is not like air traffic control. We don't tell people when to fly, where to fly. We primarily work on resource identification, resource allocation, things like that. Where am I going to get helicopters, aircraft, air crews, jet fuel, and all that from? And then when the storm approaches, it gets there, or if it happens outside the state of Florida, my team will deploy out to the field for a variety of roles. We're part of the state of Florida's Urban Search and Rescue Network, so we've worked in that capacity with unmanned systems in the past. But this is typically what we get asked to do, or what we ask unmanned systems operators to do, and that would be reconnaissance, search and rescue, no rescue yet, damage assessment, infrastructure assessment. Those are mildly different. Damage assessment is when we're just trying to calculate exactly how extensive the damage was, how many homes have been have major damage or destroyed, things like that. Infrastructure assessment is when we're actually looking at communications, water, wastewater, things like that, and figuring out what that looks like. And then mapping. And mapping data goes to a variety of consumers in the EOC and outside the, Emergency Operations Center. Number of consumers inside and outside of that. And usually what we're doing in that case is just turning that data over to the GIS department or the critical infrastructure folks, which are going to make use of that. So this is what we typically get asked to do, and depending on where we are in the disaster timeline is what we will get tasked with. Okay, the reconnaissance and search and rescue are heavy in the first 72 hours post-impact. That's what we call the life safety phase. We're just working on stabilizing the situation, identifying who needs help, and ensuring that things aren't getting necessarily worse. Reconnaissance is key. So if I go back a slide, this is how I feel really like I've got tons of time. I'm going backwards. Right, so my team was dispatched to Mexico Beach by Bay County the day after the storm. So this is landfall plus about 14 hours. And this imagery was the first imagery that the county had of how bad their coast was. Okay, when we got to the Bay County EOC the day before, I was very confused as to why everybody was standing out by the flagpole. Right? It was a nice day by that point. The storm was gone. Why is everyone standing outside? Because that was the only place that AT&T would work. Okay, Verizon, Sprint, everybody else was gone. Inside the EOC, internet's down, satellite dishes are down, landline phones are down, right? So basically, in order to talk to anybody outside of shouting distance, you had to go out by the flagpole, stand on one foot, hold your phone just the right way, and maybe you would be able to get a call out. So everybody else in the world had seen this imagery, right? Because all the news channels had flown aircraft, everything else, and this type of imagery had already gone out and said, look how bad this is. But the decision makers in the county had no idea, right? They were unable, they had not seen it yet, they were unable. So our tasking was go to Mexico Beach, get me imagery, and come back. And we did that via what we call sneaker net. Drive to the beach, take a bunch of imagery, and then drive back, okay? And then curate that on the way. So basically, as we're driving through traffic, we're picking out the best 20 images, because no one wants to see 600 images, and editing down video to get what we need. And that was actually the first time they were able to see that in the EOC and understand it. From the LAVA standpoint, and we're going to let the responders this afternoon that we worked with talk about what we did with the unmanned systems there. But we were instrumental in kind of developing a quick process in how to determine lava flow, rate, and direction without necessarily having to map and things like that. So, mission types, search and rescue. We did some of that for several storms. We'll just leave the rest of it. We fly a bunch of aircraft. Depends. Everything's commercial off the shelf. We've been doing this since 2012. We used to have to build our own stuff. That is a pain in the butt. It takes forever. I'd much rather buy it. So that's what we typically do. This is what worked. Of all the things that we do, right? Crew of 6 to 7 people, ground logistics, 10 to 12 aircraft, communications equipment, everything else. This is all that worked, right? The aircraft worked. For the most part, they were solid. They worked as intended, as we expected. There was no real surprises there, and they even went beyond what the manufacturer included. Right? We've flown DJI Mavics in 45-mile-an-hour winds. We've flown them in the rain. We've flown them in all kinds of places that maybe not a great idea, but they worked well. And then the crews, right? Our people are well trained, are used to working in environments like this. And that's a key point, right? Not just anybody can go out and do a disaster and work. That's not necessarily going to be a successful thing for anybody. But besides that, everything else you can imagine that involves deploying across halfway around the world and then going to work somewhere, that didn't work, okay? And our biggest enemy by far is time. Information in a disaster is perishable. What's true now will not be true 10 minutes from now, and it will certainly not be true tomorrow. And that in every type of equation you can think of. Not only what's the state of the disaster, but what do people need? What are the outstanding needs? What are the responder capabilities? What's the weather like? All of those things, that information is expiring as we get it. So our biggest issue is time. Everything that we do as far as gathering resources, or gathering reconnaissance, conducting searches, building maps, all of that takes time that I honestly don't always have. So that is our biggest issue by far, as well as so data processing integration. Not only technical integration, but how we integrate with EM is always an issue. Data management, we try hard and we still mess it up. Communications never works, ever, never once. Okay.
And this is with FirstNet, all this special.
Right, and every disaster in 15 years, I'm going to tell you this right now, nothing ever works right, ever. Okay, and then coordination. So I'm going to stop there because I hope if you got maybe a couple of questions, and I'm going to be available all day.
You've got
I'm also going to point out I got 36 seconds left.
36 seconds for questions.
Anybody?
All right. Well, let's see. Thank you.
All right, great. Thanks. It's up there.
It's up there somewhere. I've got to time myself too. So where's the? This is the. Okay.
The Rockstar cable
Presentation is it?
Yeah.
Yeah.
All right, well, I'm going to build on that and sort of tie in together with some resources, particularly with unmanned aerial systems, and imagery in toolkits, building on some of the previous talks that we've had. And do keep in mind, unmanned systems, you have a lot of the robots for water, marine-based, and for ground. But aerial vehicles are popular, cheap, and sexy right now, so they really capture a lot of everybody's attention, really useful. Okay, so this should be playing, and it's not. Okay.
See, it look like I made a choice not to play the video.
The keyboard.
Okay. You want to try that? To back. All right.
Oh, do you just put space, maybe?
Yes. It's supposed to be a video.
Yeah.
Right. There we go. Almost. Okay. We're so close. Yes. Play. Test this.
It's right there. We can all smell it.
Yeah.
Okay. Good job. All right. So if you saw this video, you would see a beautiful panoramic video. And what's interesting about that was David was flying that particular mission, also flying it with thermal imagery. Huge amount of data you can get from these types of events. And of course, what's motivating this workshop is, of course, the Kilauea volcanic eruption last year, or just barely. Okay, well, we'll try one more time.
Yeah.
Oh, look, all the little sparkly lights. Those are trees spontaneously combusting gas. We've got other footage where you can see the tree, it touches a tree and the tree go up in smoke, literally. Look at the extent. The geologist thoroughly happy. Look, it's rivers. Look at lava. Look, it's this. We've not seen this. From an emergency response, besides being pretty pictures and being able to know the thing, the big win for this was at nighttime, you can't fly manned helicopters and manned assets. It's very dangerous during wildfires and events to fly at night. So the only way you have eyes on is with an unmanned aerial system. And again, fast. The story he's in about the most important thing is being fast. David, when he was there, I see a lot of scientists are like, oh, we're going to take a GIS model, we'll run it to Esri, we'll do this, we'll subtract, and then 6 hours from now, we'll tell you exactly how much the lava has moved in the past 2 hours. Fly UAV, right here, GPS coordinates, come back, fly GPS, look right down, oh, do the math, oh look, in 15 minutes, you know 16 minutes, you know how much it's moved in 15 minutes. Remember to keep things simple because everything, time is at the instance. So some resources about disasters, there's some studies and tutorials that may be of value to you, and some data sets and toolkits. So 2012 was the last time. There's like a 7-year cycle of interest of everybody on things. So there was, last one was on this, the National Science Foundation, that it's a social technical system that decision-making in extreme conditions. So that's a very good reference. Everything still stands with that one. We have a webinar that I did last year for Compute for Disaster for ACM, talking about Harvey and some of that. That has a lot of introductory to how emergency management works. And if you're into unmanned systems, I have a book. But the big one, and we've talked a little bit about just for the aerial vehicle deployments. We've had 29 deployments starting with 9/11, World Trade Center. And this is giving you a base of data. And from that base of data, we've tried now to organize it because everybody's like, oh, we have all the imagery, we have all the videos. And we say, yes, here, you can have them. They go, but they're not really well labeled and organized. And they go, okay, never mind. So we have organized for Harvey and Irma. We're almost got Michael done. We being Adair, he does all the work in the volcanic eruption. So now he's going to talk about what those data sets, what they look like.
Yes. So for this, both as we said, Harvey and Irma, both you can access here. They are available once you request. And this is the data that we provide. We have, so the data would be images, videos, and photogrammetrics. And
photogrammetrics are the maps that they build out of the computer imagery.
So then data summaries like number of missions, sorties, different types of platform, as David mentioned. There is a large variety, and operation tempos, missions, and flight times. And the data set normally looks like this. And you have this kind of these colors because it's based on the missions, the types of missions that were flown. And for more details, you can access our see in our paper. It's down there. And just a quick, so you guys have an idea of the data that we collect, and you can have access. So for Harvey, We flew 56 missions with 112 flights with an average time of 10 minutes and 30 seconds. We used 9 different types of platforms, with the Mavic being the star, flown in 78 flights out of 112. As you can see, a little bit under 6,500 pictures, 106 videos. And for Michael, who's just a little bit smaller, we had 26 missions with 80 flights. The average was around 11 minutes. And we used only 4 types of platforms. The Mavic being the star again. And 11,000 pictures, 45 videos. And the size of the data also like around 8 gigabytes. And with that, I'm going to pass to Robin again.
And so just if you're, and then just going back and, oops. All right, so that didn't work very well. Right. Artificial intelligence, our natural stupidity. Okay. There we go. So if you start looking at these types of things, think about this. You now have a data set of 6,500 images of actual response images. When we worked with Berkeley and Maryland on trying to do a missing person search after a major flooding event, the only data they could get off the web was not vaguely the kind of data that you would get from a UAV. So we have this data now for you to use, and it's organized by mission. You can actually, on these spreadsheets, 11. Am I going backwards? Okay, backwards. Okay, on these you can click and it'll take you to those files. So we're trying to be more useful to you with there. Another thing that we're doing is the computer vision for emergency response toolkit, taking classic algorithms or algorithms that have been responded for and putting them in a format not OpenCV, because no responder in their right mind with no sleep, haven't slept in 32 hours, can figure out how to do OpenCV and, oh, now we got to upgrade Java or whatever. No, here, I have a Windows machine, I have files. I want dehazing. I want to look for differences. Circle this. That's the sort of thing that we want to see. And so that's what we're trying to do, is to open that up for researchers to put it in. We'll maintain the site, continue to add to things that they can use. Also, they want to download it to their own system because like you heard, there's no communication. Even with FirstNet, there's no communication. It wasn't really built to have the bandwidth we need either. So you see, you have an image, you upload your images, it runs it through. This is a difference operator. It's a machine learning program that learns what's normal or average. And then here it's highlighting in the image things that are different. So now the person can look at it and say, okay, what's this over here? Okay, yeah, that's a piece of trash. Oh, those are people. Now that was us as researchers, so great, we found ourselves. But you can start seeing the value of that. Then you can also annotate and mark whether you've checked it, and somebody else needs to go check it, and these different things. So it's all about how to make people in the field use it, but you can add to it through GitHub. So that's what we're trying to do with that. So that wraps up our presentation about some of the assets that might be of value to you. And we're actually on time. So this is a hoo-hoo to all of our presenters who are the formal. So let's take a 5-minute break, because some of us may have had a little bit of coffee. And then we'll come back and let's hear some more from the lightning talks, all right? All right, big shout out to our presenters. Yay. 11, we'll start back. 10. Or 10. 10.
Don't go back out.
Good job.
You can use the bathroom, it's just through there to your left side.
No, it's mine. Is this like this is peanut butter?
That's right.
Very good. Good job. Analysis. Getting that integrated. So the undergraduate who's doing a former undergraduate, Travis, called and said, we've uploaded it. I've run the images. these are so good. You know, it's like I don't usually get Travis to say,
I
hey.
had a question that just came to mind. Are you guys looking at intelligence inside of the actual AVs, or just kind of like you just focused on
All of the above.
all the above?
But the data to decision process is probably the biggest key.
That's the biggest focus.
But we need more, as you saw, like a convention pushes more to the edge. We need more processing.
Right.
So that the person, we pick people on teams based on whether they get Carson.
Really?
Because somebody's sitting in the passenger seat doing the editing.
Ah, I see.
So yeah, if processing could be done on board and then reduce the amount of data that's got to be, throw away the bad, give us the good.
Or done on the OCU.
Right, or near to that real time, that would be.
Or orient the AV based on what.
Right, anything we can do to compress the timeline between data capture and decision making would be key.
Yeah,
that's good.
Yeah, okay.
Yeah, so we're kind of starting to work on some of that with yes, environments. I work with James, so actually, yeah. You know James? No,
Part of ACM.
Yeah, but
Yes.
exactly.
Well, the technology is actually this whole lab. We collaborate with them.
I was just
like working for.
Oh, Christy.
Yeah, with the new building that they're going to build. So yeah, it's kind of cool.
So we're collaborating with them in the projects that we have. Visualization North. So they're really doing that. Jason Lee. Yeah. This is CyberCon is a different setup. He's got his own CyberCon out there.
Yeah, I saw the
He did. Okay, check out the Lava Lab.
Yeah.
Okay, pretty cool, huh?
Yeah, it's cool.
Yeah, it's this whole place took about 2 years to put together. And this is all student work. So. Your name was?
David.
Francis. Are you talking to? He's speaking as well.
One of the lightning
Okay.
I would like to replace my presentation file and hold on to.
Which presentation is it?
What do we have for next week?
That's very interesting. So we recently.
I'm Trisha.
Lou, nice to meet you. So, yeah, it sounds like you have a really interesting background. I'm excited to hear your talk.
Oh, thanks. I mean, we're just sort of, we've been working on a human-to-human interaction project.
The Unity program staff, that's good. Is it?
Yeah. I took a look at your presentation.
That comes independently that I can beforehand.
Yeah. So it sounds like almost crowdsourcing a little bit. I might be a little off with that.
Because it has that weird thing where if you put
from all possible sources. That's so very
important processor, you don't know what.
Interaction, but we've got people who are knowledgeable.
Look into something Thursday.
Oh, that would be.
So there's two things.
Awesome. And so at a university?
Yeah, I'm at USC.
After they're done.
Someone else, although we're at different labs.
So you didn't know that you guys were.
The name, and I went, oh, but I hadn't actually met her before. So what brings you?
So I'm staying for the whole conference, but I mostly work on factors, so analyzing sensor data and things like that, control data. Frankly, I was interested mostly in this because my partner is actually, her background is in environmental science, so we talk a lot about this program. encouraged me to come. And it seemed really interesting because it's like a field trip.
It is, and I think it's an awful main theory is to let the real people know what the real things are.
Yeah, that's definitely what I was integration relates to technology, but the opportunity to get information directly from the source, that's going to be awesome.
I see you clicking. You can just click.
Okay, a couple more people.
So it just seemed like a really unique
because you're used to it.
It's I'm used to it. I don't know which
workshops and things like that.
I think there's probably somewhere else.
Yeah, this is definitely really involved.
They really planned it out really well.
this is such a
Cool.
Have you had a chance to go there?
I just got in, so I checked into my breakfast, the Big Island, and loafed around a little bit, looked at the ocean, but haven't really done
How to use that little spotlight pointer thing.
Try it.
Later on.
You just hold
it
down.
Just point this and it does it.
Okay.
Yeah, hold it for like 5 seconds.
Are you into caving at all? Or
It's got a realization on it too. So
that's much. Yeah.
Maybe at some point I'll look more into
Yeah, it seems like Hawaii would be a great place to live.
And let's see, besides that, you have what are these, up and down? These are next slide and previous slides?
Next slide. Just have everything. And that can interface with Sage too.
Or in any direction of the environment.
That's good. Oh, what did this do?
Turn to
Huh?
Let him fix it.
You fix
Now
it?
we're going to do
One day I'm going to have to learn how to fix it because I'll probably bump it and I'll say, oh, I want
3 slides plus a title slide and in 3 minutes so that everybody can get a little bit better introduction for particularly the ones of us that haven't get to know each other a little better. Really well running on time, which does not mean you do not get to oversee your 3 minutes, but it does mean that we should have some time to chat a little bit before we head off to the to lunch and to the field trip. Okay, let's get going. It's going to be in alphabetical order. Or whatever he says. No, just start it out in alphabetical order, but not anymore. All right, so Takashi.
They would have organized in alphabetical order, but
sorry, I forgot that.
That's okay.
The sound's on and everything.
Yeah, if it's easier, yeah, I can just follow that order.
Oh, okay. Start with this one.
Yeah.
Okay.
Mm-hmm.
Oh, sorry. Cool.
Sound is
okay. Yeah, let me put it in.
Thank you.
Was that good?
So the most important thing.
Good morning.
Yeah, they can.
Miyamoto from Japan. My affiliation is Department of Civil Engineering in University of Yamanashi in Japan. My original interest is earthquake engineering, but currently I have tackled data science, and currently I have applied data scientific techniques for disaster mitigation. In this talk, let me introduce my research about disaster detection using satellite remote sensing. As you know, satellite remote sensing is very strong tool for grasping disaster situation because it's quick, direct, and wide coverage. It is widely used for detecting macro disaster like floods or sediment disasters, but it is yet difficult to detect building damage because of limited resolution. Here, here I show examples of satellite imagery. As you see, it is very difficult for human to distinguish the difference between non-damaged buildings and collapsed buildings because of its limited resolution. So in order to improve the detection accuracy, I have developed a deep learning-based building damage detection system. So in this research, there are 2 key ideas. One is first, because detection problem is very difficult task in computer vision. So I replace the detection problem with a classification problem by extracting small image pieces of each building with the use of GIS database. Then after, I solved the classification problem by spatiotemporal CNN. In this and in this research, I use multi-temporal imageries for input tensor, and then I apply 3D convolutions for the classification. So, using designed neural network models, I had the best performance comparing to previous researches. And with this neural network model, we can grasp the whole disaster situation comparing to ground truth. And now I'm tackling to improve more accuracy by designing more complex neural networks. Okay. Thank you for listening.
Okay, thank you. Next.
Just do this one. Yeah.
All right, Andrea, there you go.
This one, right?
Yeah.
Thank you. So hi everyone, I'm Andrea, I postdoc from the University of Padua. Presently I'm involved in a project that is dealing with decision theory and knowledge representation, specifically on how to embed ethical and normative priorities. So not really close to your area of interest, but many of you, as I saw, work with machine learning and deep learning techniques. So perhaps some of you could be interested in algorithm portfolios. So basically an algorithm portfolio is a framework where you can, where the framework chooses the right solver for among a bunch of available ones to solve a specific given instance of a problem. The problem can be whatever you want. I mean, a classification problem, a SAT problem. And the idea is that the feature vector is crucial for the task because the feature is a representation of the problem. So thus the computation of the set of features, the feature generation process can be very important because different feature vector, this different feature representation of the instance can perform very differently for the same solver. So the feature generation process is fundamental, but can be also very tedious because most of the time it is manually crafted. It is also a very time-consuming process sometimes, and it needs knowledge. It needs knowledge from the machine learning techniques, but it also needs knowledge for the domain and understanding. So the deep learning approach is a first attempt to skip, to avoid for the feature generation process, to skip the need for an expert by using all the information from each instance of the problem. So basically, the idea is to use deep learning techniques, okay, to extract information from each instance, and to reduce, as I said, the human component. So basically, the idea is to transform each instance of the problem in an image, let's say a JPEG, a PNG, a BMP, whatever you want, and then use these images to train a deep neural network, like the convolutional neural network, which is the state-of-the-art system for image recognition. And then use these images to train the algorithm portfolios to choose the right solver for the specific instance. So if you are interested in how it works, please talk to me later. Thank you.
So we have to figure out, Andrea, or if Takashi is came the furthest for this one.
You get the prize.
Is it Betsy? All right, Harry.
Okay. I'm Harry Mackworth from Performances Corporation, and our primary focus is artificial intelligence for operations and logistics. Which one's the next?
Yeah, the middle one.
The middle one?
Yeah.
Okay. And there's primary two areas that we focus on this with. One is intelligent guides, as in TurboTax. So if you imagine an organization of disaster response had applications that can guide employees through processes like TurboTax. But wouldn't it even be better if those applications could be developed by subject matter experts without any programming? The other focus we have is with operationalizing data analytics. So with that, you imagine having data that people are unfamiliar with. Like, for example, principal component analysis. For most folks, they think that is how you fix your stereo, right? So imagine if you had a tool that could help people who are novice in those type of areas. So the disciplines we work with in that area are knowledge capture and representation for guidance purposes, generative tech, so that's to provide just-in-time instruction, and HEI, so that the actual people, who are the lay people, the workers, can actually play in this. So let's quickly talk about a few projects we have in this area. One is we have a project that's funded by National Science Foundation, where we partnered with North Carolina State University. And the purpose of that is to better exploit the volunteers that converge at a disaster. And with that project, we're providing knowledge capture support and some natural language understanding technologies for the corpus from the interviews of the workers. We also have a project funded by National Science Foundation also that's trying to determine how food networks can deal with the disruption from disasters. And even man-made disasters like government shutdowns. Anyhow, so with that one, we're also providing similar technology as we're doing in the first one. Another one is we're assisting in a collaboration project that's a partnership for innovation by National Science Foundation, where our objective is to create a smart system that will help food banks operate smarter. And so with that one, our responsibility is, again, knowledge capture, but we're also creating a smart engine that will help operationalize the data. Now, a real cute part of that one is we're trying to learn from the decisions that the operators make and funnel that back to make the algorithm smarter. And lastly, a project we're working on continuously is with utilities. And with there, we're trying to provide intelligent guide. A good example of all that is some of the recent fires and what impact those have had. So finally, quickly, we have these particular technologies that we think are great collaboration for research. The most important one is intelligent objects, where you can imagine if a subject matter expert can drop a procedure object into a graph and have it do all the magic stuff. So thank you for your time. That's what we do.
Thank you. All right, David.
There you go.
You can sit on
Do I make it
so you know.
full screen?
Yeah.
Hi, I'm David Takayama from Oceanet. Oceanet is a local Hawaii-based company. We call ourselves a mine-to-market company. So whatever we develop, we try to push to get it into the market. We have offices in California, Houston, and Washington, D.C. as well. So we have two parts of the company. One is the research part, and one is a consulting group. I come from the consulting group. The research guys do much more interesting things in strong AI and other stuff. But about 3 years ago, I had, what's it called, midlife crisis. And I got really bored. And so I've never written a research grant before, but I just said, oh, I'm bored. I want to write a research grant. So I wrote a SBIR research grant for the Department of Energy. And they're interested in this, basically, after a disaster, when there's no power, no communications, difficult access. They're interested in getting power up as quickly as possible. You know, without power, power is, you know, not only money, but health and safety. With, you know, results in clean water, it results in the ability to have cooling or environmental things that affects lives. So they want to get power up as quickly as possible. So we proposed to use some integration of technology, some things that we've already developed within Oceanet. So we had a system called Mercy. Mercy is a damage assessment situational awareness platform, and we're using that in Hawaii. The county of Hawaii used it for Tropical Storm Iselle. But that's basically a situational awareness platform. But we decided to mash up technology, including machine vision, to help integrate and make better decisions. So one of the issues is that after a major disaster, typically it's done manually using more manual damage assessments. More recently, people are using drones and UAVs. But even with using drones and UAVs, one of the big issues is post-processing review of data. So what our technology does is basically uses machine vision to help identify things like down power poles. We're working with utilities in Texas, for example, AEP. They're interested in, they said if we can, within the first 12 to 24 hours, if we can just identify which poles are down so that they can more efficiently allocate their resources really quickly, that would be a game changer for them. So we're in the process now of, we're collecting a lot of data to train our model. And we're working very closely now with developing ConOps, concepts of operations, with the utilities. And really, it's the technology is not the biggest hurdle. It's like developing the ConOps and making something that's practical and useful. And that's what we're working on right now. So we're very interested in working with other people and getting data and collaborating. Thank you.
All right, Trisha, you're up.
Hi everyone, my name is Patricia Chafee, but you can call me Trisha. As I said, I'm a student at USC, and presently I'm working at the USC Institute for Creative Technologies. We're working in partnership with ARL. So our project right now is looking at human-swarm interaction, and we've opted to approach this from a search and rescue context, as we believe there are many challenges that in search and rescue that human-swarm interaction can assist with. In the future, we believe that humans and robots will be sharing the field, so it is imperative that they be able to effectively communicate and collaborate with one another. So to give you guys a brief project overview, some of the challenges that we're seeking to address with our human-swarm interaction project is taking care of the issue of overburdening of human operators. This is a challenge in search and rescue as well, as you have a lot of data coming in. So we're hoping to help with that with our system. In addition, we want to try to address the challenge of real-time planning. As some people have already mentioned, communication is sporadic and not predictable in a disaster zone. So if our autonomous robots can behave appropriately and effectively, even without real-time updates, that is a very useful feature. In addition, we want to look at effective communication with different humans. For a swarm operator or a disaster responder, it would be appropriate for them to assign a task to a robot and expect it to behave in the best way. However, for a civilian, it might not be as appropriate, so it's important that our robots be able to recognize who they're interacting with. To address these challenges, two of the approaches we're considering are here, the first of which is a sports team-inspired playbook. The idea behind this is that our robots would have a high-level set of commands that they would implement in their sort of exploration of a disaster zone. And so even when communication is down, they're still working to assist people. The second approach we're looking at is that of a virtual swarm spokesperson. The idea behind this entity is that it assists with collating data and presenting it in more palatable form to the human operators working with this. Our year-long goals are to create a framework for experimentation and data collection and to have a demonstration in a simulated environment. So in our current status, we're working on building a simulated scenario for wildfires. As I'm from California, that's very relevant right now for us. We're proceeding with building the virtual reality environment, so acquiring assets and laying down the foundation. And from this workshop, we're hoping to get insight into how disaster relief is conducted now and how those directly responsible expect it to change in the future. In addition, we'd like to identify areas where human-swarm interaction can best complement current practices. And finally, we hope to find or identify challenges that we might not have anticipated or have sort of unobvious solutions. And that's my time. Thank you.
Yes.
It's kind of neat. Everybody gets to kind of look up there and see if they recognize their title slide to see if they're going to be next. Yeah.
All right, so my name is Lou, and today I'm going to present a case study that I've worked on regarding anomaly detection on time series data, which is particularly relevant to this field. As mentioned before, oftentimes before bad events, you often have anomalies in either sensor data or any other data that you're collecting. So let's start with what's been happening before, which is oftentimes when you collect sensor or time series data, it'll look like this. And if you try and do a lay anomaly detection method, kind of out of the box sort of deal, you'll find anomalies all over the place in locations that may not represent things that precede failure or catastrophic events. So what I'm going to explain is how we work around that. So say you have data that is either labeled in a supervised way or by some sort of heuristic. So those green lines represent boundaries of specific events happening. So in this case, it's cyclical data, and each green line you see there represents the boundary of which another distinct event is happening. So once you add those boundaries, what you can do afterwards is if you have any sort of other heuristic, like when activities are, when the periods are inactive, or when you want to remove data that is not relevant, you can do that and you get a much cleaner signal. You can then apply principal components analysis. This is skipping a couple of things, but you can then apply principal components analysis, and what that does is it compresses all of your diverse signals into one or two components, whatever you choose. So you can see you have a much more smooth out signal at this point, and because you've identified your boundaries, you can actually pull out your individual time series like this, this is the step where you actually determine time series features. So you can look at each one of these individual time series and you can determine things like what the entropy or the curvature or autocorrelation or other time series features are. And you can actually create a matrix per individual time series. And from that, you can detect anomalies by visualizing them on a 2D plane. So here, let's take a look at one of these in the corner here. So that's an anomaly right there, which may have not been detected using traditional methods, and it's not good. So that's it.
Thank you. I like the not good emoji. I really like that.
Yep. So it's this one, right? All right. So they asked for a few slides, so I skip the introduction. My name is Daniel, and I work at USC with the Yolanda Information Science Institute, and I work at this model integration project that well, it's a huge collaboration among universities. But well, the point, the reason why I'm here is well, analyzing the impact of disasters. in a society actually requires model integration, even though in the beginning you might say, well, what is really model integration related to disaster analysis? And I've pasted here a sample question of the questions that modelers might ask, which is, well, given a precipitation forecast, what is the risk of flooding and what will that impact my crops, which is what I care for in the end. And if you start analyzing this, well, you see that now you're talking about weather, you're talking about flooding, so that's hydrology models, and you are also talking about crop production, which is agriculture. You are asking all these things in the same question, and well, you actually need to see not how these models perform separately, but how they integrate and affect each other, right? And what we are doing in the project is trying to address these challenges, but the problem is that there are many, many different things that you have to tackle. First, you need to find the appropriate data, which is whenever you are trying to assess a disaster is very, very important. Then you need to know what are the compatible models that this data can be fed in. How can we do the actual transformation and data preparation from the data that you have, which often comes from official sources such as NASA, into some of these models that require very specific variables and data transformations, right? And then you need to address, well, spatial and temporal mismatches in the data and in the models, adapt the grids of one model to the other model, and in general, well, also model calibration in general, many, many challenges that often take most of the time of modelers when they want to answer some of these questions. And what we are doing, what we are proposing in MINT, is to address these challenges by using semantics to capture the metadata that describes both the data and the models, the software, and how to run them, so we can facilitate, well, we would like to fully automate, but being realistic is more facilitate the integration and reduce the amount of time that really takes to support, set up, and run all these different models together. This includes also doing some automated planning for the addressing the different transformations between components and applying machine learning models to complete the data that we might be missing, for example, when we need to calibrate the models. And this is where we are at. I'm not going to go here in detail because I'm running out of time, but the idea is that we present this dashboard to users that they can use to set up, select their data and models, and answer their questions more efficiently than they are currently doing now. Because this is model integration is a process that usually takes them up to years at the moment, depending on the complexity of the models and the questions we are dealing with. Thank you.
Great, thanks. Is it possible to pull up the live version of this in Google Slides? Is that an option?
Made a few changes. Is that okay? Oh yeah. A lot longer. That's okay. But yes. Future. So it's on Google Slides. I think we have to log into it. Is it? Yeah. Oh, I think.
Because yeah, the link, it's not. We can have the next one maybe. Then.
Okay.
So.
Is there one more?
Yes. Jason. Let's see. Next to participants.
Huh?
Next to the folder participants on the left.
Yeah. Here. Oh, okay. Sorry.
All right, good morning. My name is Jason Levy from the University of Hawaii at West Oahu. We're very delighted to be here. In fact, we have the only undergraduate disaster program in the UH system. It's called Disaster Preparedness and Emergency Management. And in fact, we are reconfiguring the entire program to deal with the topics that we're discussing today. In fact, most recently, the students and I put together an IEEE conference at the Manoa campus that dealt with computational intelligence and computer networks. And this is our most recent book on extreme emergency management. It's sort of a term I came up with that brings together a lot of these concepts. Of course, the Germans have extreme manufacturing. You hear about extreme 5G, extreme communication, extreme computing, extreme data. So of course, we need extreme emergency management to deal with all that. So that's what our students are learning about. And in fact, just an hour after I spoke with Dr. Murphy on Thursday, I went to class, and in fact, we were watching one of her videos because disaster robotics is very essential to all the things that we're doing. Now, as I said, we're a little bit ahead of the curve because at least in higher education, especially when you're dealing with underserved communities, machine learning and AI isn't the first thing that they have been exposed to. However, we feel that we want to give them a running start in life, and so we're willing to take this risk. Traditionally, disaster studies, homeland security, emergency management type of programs have been focused in the social sciences, University of Delaware, University of Colorado at Boulder, etc. All right, so this is, again, this comes from our book, but we also have an MIT Fab Lab, one of only two MIT Fab Labs in the state. And one of them is actually in my office. And these are some of the things that we've printed off. Small drones. In fact, that's the TSA key, master key. If you look at, and of course, this completely removes the supply chain, right? If you're able to print off emergency supplies, you no longer have to be importing things from China to remote locations. So you could print off, as you can imagine, that specific wrench, which we did. That prosthetic is a little pathetic. I just gave you an example of a plastic, piping there. But just for example, that wrench could be is now printed with bronze powder, and you can have like any ratio of bronze to plastic that you wanted. Okay, and then this is again our paradigm of extreme, disaster and emergency management involves higher degrees of automation, high task complexity, and higher consequences, and we tend to deal with these type of emergency services. And so what we're doing is we're trying to put all these concepts together, and then we found that this has had a very this of course has had a very profound impact on our students. So we're carrying out some type of quasi-experimental design with pre-test and post-test to see how actually implementing the theory and the practice of all of this can help to transform their education. The other thing I have to share with you, the time is increasing. Yeah,
because you're over.
Right.
Yeah.
Oh,
you're over time now.
All right. So the final thing I'll tell you is that our campus is the fastest growing in the nation and has the largest percentage of indigenous native Hawaiians in the world, in our neck of the woods. Thank you.
Great. Thank you.
Can I stop talking? Oh, that's our interesting. This one. Is this one? Let's. Oops. Yes.
Abu, you can, yeah. So yours.
Try it one more time. Okay.
Yeah, thanks for running that. All right, thanks so much, guys.
We have too much semesters.
Yeah, Windows doesn't like putting things on multiple screens, so you just kind of have to. Awesome. Okay. This is the okay. Great.
Let's see if it works.
Okay. So, maybe we can start the present mode that way. Yeah. If I find presentation mode.
Oh, then okay, then maybe I can just ask you to go down and we can just keep it here and then we can go down manually if we need. Yeah, okay. Yeah, thanks for bearing with me, guys. All right, good morning. It's been a real pleasure to hear all of the talks so far. Wow, I'm already at 2 minutes. Okay, well, we'll make this work. So my name is Abu. I am also inspired by a very similar problem that Lou mentioned, which is that a lot of like out-of-the-box standard time series analysis techniques don't work well when you have complex time series data, such as what we encounter sometimes with seismic data and geosciences data. So what we're proposing is a new technique called contrastive singular spectrum analysis that marries together two important ideas. And I'll mention what those two ideas are, and then I'll talk about how to apply them. Can we go to the next slide? So the first ingredient is contrastive analysis. So normally when you use unsupervised learning techniques, you try to get whatever the dominant structure in the data is, the dominant subsignals in time series data, or the dominant axes of variation in PCA. Contrastive analysis instead says, let me find the dominant structure that is present in a data set, but that is absent from a secondary data set that I'll call the background data set. Okay, the second ingredient is singular spectrum analysis. For those of you guys who work with time series data, you're probably familiar with this. It's a way to decompose a complex time series into much smaller subsignals that carry kind of the variation of interest. Okay, so contrastive SSA finds subsignals in the same way SSA does, but those that are enriched in a particular data set compared to a secondary data set. So this is a very, very simple cartoon. If your target data set has these two subsignals in it, and you have a background data set that's the following, SSA will just find the dominant subseries, but CSSA will find the kind of the one that's enhanced in the target relative to the background. This is a very simple schematic. In reality, CSSA finds much more complex signals and kind of those that are more nuanced. Why might this be useful? If we can go to the last slide. These are just suggestions. I would love to get more input from people who work in the domain. But the idea is that, for example, let's say you're looking at seismic data that has certain kind of a lot of complex signals in it. If you just do SSA or a standard technique, you'll find all sorts of signals. But you're probably more interested in things that are happening, those subsignals that are present during natural disasters that are not present in normal situations. So you can do these contrastive techniques to find what those signals are and better kind of understand what makes a natural disaster a natural disaster from the point of view of time series data. Thank you very much, and I'd be very happy to chat with more of you guys who kind of collect this data and work with this data to see what we can do. We have a paper that has a lot more details. Okay, thank you.
So these are all the PowerPoints, so we're good time.
Great, everybody's done really well on staying on time, so that's super. So any surprises? Has anybody learned something that they didn't know about before? Yeah. Everybody knew everything? Okay. Let's talk a minute as we think about questions to ask each other. We've sort of put the group learning or the breakouts into the deep learning, computer vision, that sort of stuff. Another one is on unmanned systems. Another on with geo, just all things related to GIS, geosciences. And another one related to decision aids, decision making, decision aids. So that was just based on what you all sent, how we grouped them. Do we like those 4 breakout topics? Do we see a different clustering? Again, we're taking advantage of this to write a report that Yolanda will most likely include in the bigger report. They could really influence how funding is. Is there another way to partition it? Suzanne?
Well, just one more thing that I think is really important is that idea, and I don't know, the idea of having a core platform to support it, that you can build the applications like that.
So that's a gap in research, the lack of tools.
Yeah.
Now, is that a way we get these different intellectual topics, or is that an enabler, or is that itself a research area? So definitely we want to put tools test bed. Anything else in that category of toolkits, test beds?
Data.
Data, where's the data coming from?
In some sense, you want a playground where you can plug in new ideas and new components. After the Hawaii 2018 workshop, we were calling it the sandbox that we could play in. Yeah.
Okay, interesting. So that might be an interesting cluster to have, even though it would be cross-cutting of all of these. Because that's really, isn't that fun to see the multidisciplinary aspect of all of this, right? And I thought Alice did a really great job of saying, you know, there's time we do computer vision, but there's the stuff, you know, oh, we make it pretty for us to look at, but the actual users are going to be using computer vision algorithms, which we know we can accidentally interfere with in the way we do that. The same thing with the data, the way we process it, there are people with boots on the ground that have to actually use it. So how do we do that? All right, so are there any other clusters or ideas that you felt emerged? We can have that here.
Question about human-computer interactions, not specifically stated. Do you think that would be on a decision or on a where? Is that a separate area?
Yeah, we saw that a little bit in unmanned systems. We saw that a little bit in decisions. We saw that in the swarms idea. Yeah, there's a human. What's nice, there's a human in there somewhere. Even though this is AI, there's a human in there somewhere. Lots of them. You know, that people want to consume the information, or people providing, or people who need the impact of the AI stuff. We think about. You know, we'll also see today. I think in the field trip we'll see there's also these the middle managers, the emergency managers who have to worry about public accountability. Do I use an AI system? If something goes wrong, then it makes the county, it makes the city, it makes the state, it makes me look stupid. Why would I do that? People would say, why am I paying tax dollars for this debacle? And that's another set of HCI and a different way of thinking about it.
So maybe we have decision, it can be something more like a distributed, collaborative decision making. Because I think I also heard these themes of, you know, different people have different information, there's not enough communication, a very specific kind of collaboration and decision making and distributed agency.
Right, and a lot of stuff, and for lack of a better word, heterogeneous. There's no one decision, right? There's at least 14 emergency support functions. Everybody's looking at the same data, but has very important decisions to make that are quite different. You know, what you want to do if you're the people trying to get roads open, for the responders to get in, for relief supplies to get in, is very different than if you're looking at something like, you know, fire rescue, or if you're worried about, oh, somebody needs to get enough porta potties in, okay? Which trivia that usually falls to the Forestry Service, the federal agency with the most access to porta potties in the United States. Who knew? All right, so distributed decision making, collaborative, how we do that. I think that was also another theme we kind of began to see creep in, is that we're not looking for fully autonomous, handed over to Skynet level of AI to solve all of our problems. It's decision assistance. It's more helping the emergency managers deal with that. And every disaster is different, right? Everyone has their similar. Hurricanes can be quite different in their impact. David had alluded to windstorm versus surge. Harvey in Houston was all flooding. There was very little wind damage. There was some, but extremely limited. Whereas other ones, it's hugely wind damage and less water. So even though they're hurricanes and they have a certain same category rating, the impacts are totally different. What else do we see? Any other clusters? These are great to start thinking about it. Okay.
Yeah, interestingly, a few different people had specifically time series related algorithms, so there are, as algorithms, they're related to deep learning, but I don't think these particular algorithms were actually deep.
They seem like they were more in the geo.
Yeah,
That's how I put that. Was how I was thinking that those might go in.
Actually, that makes sense because I think that it's good for algorithms, people who talk to algorithms, people, but it's also useful to go beyond that and talk to people who deal with the data or the decision making. Yeah, so I agree.
So, Andrea?
I think that deep learning is a restriction for a more broad cluster, which is AI systems or AI agents.
Yeah, but I'd call it an unmanned systems an AI agent. Decision making could be an AI agent. So I think you've got something, but maybe we could flesh it out a little more.
Maybe human in the loop.
Is that what you're thinking? So besides there's a learning stuff, but there needs to be an idea of agency and a human in the loop. What are you thinking, Atlas? This is where.
Well, I really agree with Andrew that deep learning shouldn't be the only focus we're talking about. Well, computer vision could be with general tools as well. So
this would go under the computer vision would be the bigger cluster.
Not necessarily. They need to be contained to each other. That could both serve the unified purpose of perception.
Maybe machine learning instead of deep. Is that what you're looking? That's too broad.
Well, isn't it interesting? Perception. So we're getting back to the idea of a certain type of sensory data. And data is so important. But more important than data is information, right? Data, that model, that data is the raw stuff. Information is where it's been formatted to support a decision. And the actual decision is made by a human who has knowledge and can take that. And of course, if you give them data, they have to create the information content themselves, which doesn't work as well when they're sleepy and tired, or the data is just so big they can't do it. And that's always been a barrier, and that's the standard industrial systems model of the data to decision process.
So one comment that I think several people brought up is the need for timeliness. That could be cross-cutting, but that's something that needs to be addressed.
Yeah, that time pressure, and that was one of the things in the crisis. The 2012 NSF study said the time criticality on this, the scale of the data is extreme. So going back to Jason's talking about extreme timescales because they're often extremely compressed. The life-saving phase, your life-saving's over in 52 hours. The inflection point, and it's actually even earlier because you may be pulled out of the rubble alive, but you may have injuries that will stay with you the rest of your life. You will be permanently impaired or have health problems because you have not been found quick enough, right? It's really more like 12 hours, which you really like. It's another big inflection point. So you've got this whole idea of time pressure, but you've got scale. I mean, like an earthquake can affect multiple states, a hurricane multiple states. So you've got a spatial scale. You've got a temporal scale of what are the long-term effects that you're seeing, so many of you are seeing with all of this. And all of these scales come together. How do you do that? It's no one thing. So time pressure is an important thing.
Well, one other area, and I'm putting my industry hat on here, is knowledge representation and knowledge capture. What we find is the biggest issue, particularly on the cognitive side rather than the data analytics side, is getting information from the subject matter experts. Like in the food bank project we're working on, the food bank folks have their own tasks. They're demanding their time. And we get them to sit down and do a dump of their knowledge so they can use the smart system. It's probably the biggest out there.
Yeah, the knowledge engineering.
Right.
We've come full circle back to the early days of AI, right, to the 70s and 80s. We were doing a lot of knowledge engineering, and then we walked away from that, and now it's there. Interesting, one of the things I really like that I heard that we're seeing, I think, is that we're beginning to see, while we have all this on deep learning, we saw the word semantic show up quite a bit, right?
Yeah.
And that's nice, for things that typically are not looking at semantic to semantic, and they're both in there somewhere. So, Jason, you had something.
Yeah, I was just going to say this is all really powerful. I'm sufficiently old that, of course, back in the day, the holy grail of AI was like deep AI, right? Generalized AI. And now we prefer the term IA, some type of just intelligent augmentation for, for human activity. The other deep thing I wanted to share is that from our experience, it seems that these systems have to be fully embedded, something they're called like enacted systems. So, behavioral-based dynamic interaction with the environment, where sometimes the agent, changes based on the environment changes based on the agent. So in the old days, the concept was that you just needed some, some production rules, right? The symbolic approach. But now we recognize you actually need a body, you actually need a robot to actually do all of these things, to gain this real-time knowledge and to evolve and to be and to promote self-organization and create an active, functional, autonomous, embedded system. I'll shut up.
Yeah, I'd say that physical situatedness, the idea when you're talking about unmanned systems. So with UAVs, you're hoping to have less physically situatedness in terms of collisions where you're taking out a landing and more of that sensing and perception. All right, well, let's see if we can group those. We'll talk about that. We're at the 11 o'clock mark, right at, so we'll probably want to start rethinking how we're going to divide up. We still have enough cars. Okay, great.
So we have 3. So you just have to split now. Yeah.
Okay, so and we're going to go to Heroes, which is a buffet cafeteria not far from here, and it should be able to accommodate all food types of preferences there. He's looking at me like I'm crazy. Well,
anyway.
Well,
it's kind of like traditional Hawaiian food. Basically.
It's traditional Hawaiian food, but if you've got something, you can find something to eat there if you're a vegetarian. If or if you're a hardcore carnivore, you can find that. Do you have our clients? Are there anything they should be looking for? What Noco Loco, Masubi, anything in particular? Okay. Well, anyway, so we'll do that, and so we'll start. We will not be returning to this room. All right, so we take up and go, and we won't be returning to this. We are at the portables at noon, so we'll all go over. They has outside seating, so we'll just all hang out there, and then we'll all leave. We'll caravan at 12 to go to the portables. All right.
So I have a suggestion, a request, or both. So I think it would be really helpful if each of us, as we interact with the first responders and as we learn more about the problems and how things work, if each of us comes up with 3 good research problems from our perspective, right? And then when we come back, maybe, or when we talk again, if we share those, if there was any way for us to share those, and then cluster them together.
Yeah, that may be a good way to redo the breakouts.
Well, not necessarily redo, but we could assign these research questions to the different breakouts and we use them.
So I assume everybody has, little wireless apps, in their phones. So email, research app, where you've been doing, and we'll try to sort those on the fly. Okay. All right. So we've got blue shirts. We've all got minivans. Each one has a minivan. So let's take a few minutes and meet down. Should we meet downstairs in the library? And then thank you for your help.
Get excited if they do that.
I will not be physically present.
Okay, we're going to the bottom floor of the library, but we're not going outside into the kiddie stuff. Okay, we'll meet out there, and then we'll break up into our groups, and we'll serpentine our way through the booths to our assigned shuttles, okay? All right, good job, everybody.
I'll try to general myself. That is your attempt. That could also be a part of a grant. For some generalization. So we talked about it's very specific. And
So it's like hardwired into the code.
Okay. I'm trying to do some general, so I still need to do a little bit of learning. This worked pretty well.
By the way, we have a 4th